Okay, next we will discuss about traveling wave. First we will define traveling wave. The wave which transfer energy in moving away from the source of disturbance is called traveling wave. So it means that any kind of wave is a traveling wave. A wave is basically a disturbance uh, which moving from one point to another point, and during that moment it carries energy. Now, example of traveling waves is are waves on a spring, waves on a spring, or in a string. Suppose we have a string which is connected to a support and we are moving it up and down from one end. Then we have wave creating in this way, string in this way. The wave are moving in this direction. Let's suppose this is the x direction. Then the particle of the medium, which is the particle the string, are moving up or down. Now this small portion from one minimum to another minimum, here this one, is called a pulse. So I will consider, let's suppose we oscillate the string upward, then we create this pulse. If we oscillate the string downward, then we are creating this pulse. So these oscillations are continuously because we are oscillating this string up and down continuously. So due to this continuous oscillation, we have wave pulse creating in this string which are moving in the forward direction this way. Now suppose I will consider only one pulse. This is the direction of this is the string, and suppose we have created a pulse in this string. This is one pulse, this pulse. Which is traveling in this string in the right direction with a constant speed, which is moving in this way with a constant speed v. But remember that v is constant. Now the wave pulse is moving along x-axis while the displacement of the string is along y-axis. The displacement is along y-axis because pulse is moving in this way while the string medium of the particle are moving up or down. So its displacement is along y-axis. Now the displacement of this string, this displacement depends on the x coordinate and time also. If the displacement here, then if we consider x this point, then the displacement is this one. If we consider this point, then the displacement is bigger. If we consider this point, the displacement is this one. If we consider this point, the displacement is this one. If we consider this point x, then the displacement is 0. So we consider a point P where the displacement along y-axis, which is a function of both position and time, okay, which is equal to a function of x because it depends on the x-axis. If we are here, the displacement is this one. If I am here, the displacement is this one. Now that this is the pulse we create at time t is equal to 0, like the initial pulse creating in the string. Now this equation tell us about the shape of the wave. Like the vertical displacement, the y displacement of the medium particle length y exists depends on two coordinates. Now one is x and the other one is time. If x is this one, then the displacement is this one. If x is, by changing x, the displacement also changing, and also with time the displacement also changes as it moves in the forward way. So we have this y displacement, which is a function of x. Now this is initial condition, like the wave just the pulse creating in the string. Okay, now this pulse after some time move forward. Suppose this is the initial pulse. This is the initial pulse, which after some time reach to this point. This point. So this point P, this is the point P, which I consider this one, okay? Point P. Now move from this point to this point after some time T. So here, the distance from this origin to this point P is x. Now again here, the distance from this point origin to this point is x. While this distance from here to here, I call it x prime. Since we are calculating this much distance s, which is equal to, because velocity is equal to distance per unit time, so s is equal to vt. So this displacement will be equal to vt. Now after time t, the pulse reached to this point, so its displacement of the particle, which is a function of both position and time, is now equal to a function of x prime. Because at this point P at this location has a different x, while here the x-axis was different. So here we represented by x, so here we represented by x prime. Now if you look at the figure, from this figure, this x, which is this one, this is basically equal to this one plus this one. So x is equal to, this one is x prime and this one is this vt plus vt, or x prime is equal to x minus vt. So if we put it in above equation, then we have y is a function of x over t is equal to f of x prime minus vt. This is a general equation of a pulse, a wave. This is a general equation of a wave. Now, at any point on this wave, we consider any point, like any point, which I suppose to be point P. Any point P on this pulse, on wave pulse, is called phase of the wave. Any point, if you consider this point, then this point is called phase of the wave. If someone considers this point, then that point is also called a phase of the wave. So if someone considers this point, then this point is also called phase of the wave. Now, once we consider a point on this wave pulse, then that point will remain constant, because this point, which is here, now move here, so it's remain constant. So it means that this x prime, because this is the pulse point distance, x prime, which is equal to x minus vt by this equation, is equal to constant, because the point does not change. This point is here, it was here, it again here, so it doesn't change. Once it's become constant, and if we differentiate with respect to time, we get dx prime over dt is equal to d over dt of x minus vt, which is equal to constant, so which is equal to 0 because the derivative of constant is 0. Now here I already told you that this pulse move in this direction in the forward way with a constant velocity. Velocity is constant. So once velocity is constant, if we apply this derivative to this one, then this will become dx over dt minus velocity is constant. So we apply this derivative to this t, dt over dt is equal to 0. From this we get dx over dt minus v is equal to 0, v is equal to dx over dt. Now here dx over dt is equal to v is the velocity of the phase. It's the velocity of this point P, and we call this point P as the phase of the wave. So it's the velocity of the phase, and it's called phase velocity. This is the phase velocity when wave pulse moving in positive x direction, because the wave pulse move in the positive x direction this way. If the wave pulse moving in the negative x direction, if wave pulse move in negative x direction, then the phase velocity v, the phase velocity dx over dt must be equal to minus v, because its direction is opposite to v. Here the wave pulse move in this way, here the wave pulse move in this way. So this is the phase velocity. In the next video we will generalize this more by considering a specific wave. Thank you.